talk about 3.7 here, rational functions. So let's state the zero factor property first. And you'll notice that this video is a little different than most of the rest of it. It has a lot of stuff typed up. That's because there's a lot going on. You can actually find a version of this on my website. And you can have all these notes for yourself. But let's go ahead and get through this. So first, let us state a property we've used multiple times already. It's called the zero factor property. The zero factor property, I call it the ZFP. And it says if multiple terms are multiplied together and set equal to 0, then one or more of those factors must itself equal 0. So I say, consider the factored polynomial equation 2 times x plus 3 times x minus 4 times x plus 1 squared equals 0. We could expand that term using repeated applications of binomial expansion, that is, just FOIL everything out. So go through here, distribute the 2 into everything. Then distribute this 2x through both of these terms, and the 3 to both of these terms. And then we'd have some huge quadratic out here that we could simplify, and we could square this thing and do x plus 1 times x plus 1, and do all that if we wanted to. But we don't want to do that. Nobody has time for that. Instead, we're just going to apply the zero factor property. Since all those factors are multiplied together, we have that each factor must itself be equal to 0. That is, we have that either 2 equals 0, so either this is 0, okay, either x plus 3 equals 0, either this term, x plus 4 equals 0, or x plus 1 squared equals 0. And so going back to some of the multiplicity stuff that we talked about before, we obtain either x equals negative 3, okay, that is, solving this, we get x equals negative 3. Solving this, we get x equals positive 4. And then solving this, we get x equals negative 1, but twice. So that's what this means with multiplicity 2. Also, note that since 2 equals 0 makes no sense, so we ignore it. But that is one of the things. You set it equal to 0. But we ignore it, so don't worry about it. So we found the solutions without doing any nasty multiplication, and that's cool. And another way you can think about this 2 equals 0 thing is you could take this equation right here, and you could just divide both sides by 2. If you divide this side by 2, the 2's cancel, and you're left with just 1. And then 0 divided by 2 is, well, 0. So nothing really changed. So in that way, it didn't matter either. So let's skip on and get to the actual thing that we're here to talk about. This is something you're going to need to keep in mind, though. So now we're going to talk about rational functions. So we're going to simplify and discuss 4 identifying features of a rational function. That's their horizontal intercepts, that is their x-intercepts, the vertical intercept, that is the y-intercept, the vertical asymptotes, and the horizontal asymptote. And we'll discuss the methods for finding each. All right. So for example, we're going to consider the rational function f of x equals x plus 1 times x minus 2 over x squared minus 10x plus 25. And in general, a rational function has a particular kind of look, and it is, a rational function is f of x equals p of x over q of x. Okay, where p of x and q of x are both polynomials, and q of x isn't 0, for obvious reasons. So a rational function is just a, well, it's a, look at this, ratio of functions, polynomial functions usually in specific. There are rational functions that can use square roots, that can use natural logarithms and whatnot, but those aren't these kinds of rational functions that we're talking about. And there's plenty of mathematicians out there that would classify them utterly different. And to those people I say, hey man, that's fine, you do you. All right, but let's talk about this one in particular. And this is what we're going to talk about for a while here. So write that down, keep it in mind, and we're going to move forward. So to find the x-intercepts of this, we're going to set the whole rational function equal to 0 and solve. Now think back to any other function you've ever had. If you want to find the x-intercepts, that is the place where this thing crosses the x-axis, that's where y equals 0. If you've got, think about it, I'll do it in this little space right here. If you've got your x and y axis and you're wanting an x-intercept, like this point right here, of course your y distance is 0. Your y distance, this distance here, is 0. You haven't went up or down from this point. And since you haven't went up or down from this point, neither up nor down from this point, then your y must be 0. Well, your y is your output, of course, the thing that you get. So what you say is, well, I want to take my function and I want the output to be 0. So that's what you do. You take the whole thing and you say, I want the output to be 0, and that's going to give you what we're doing. All right, continuing on. It says, starting here, note that the only way that the function above can be 0 is if the numerator is equal to 0. And think about that. If the bottom here, if the denominator is equal to 0, well, then we're dividing by 0, and that's bad. We can't do that. We'll come back to that in a minute. That's actually how you get asymptotes. However, if your numerator is equal to 0, then your whole thing can be equal to 0. So all you have to do to find the x-intercepts, okay, is that you just set the numerator of the rational function equal to 0 and solve. And good thing is, the rational functions that we're dealing with, indeed all rational functions that ever have mattered ever, are going to be polynomials. So it's just going to be polynomials equal to 0, and you had an entire class on that. That's what most Algebra 2 classes cover. So, of course, we solve this by the zero factor property, and we get that either x equals -1 or x equals +2. And, I mean, there's no real math to be done here. You're solving x plus 1 equals 0. You subtract 1 from both sides. You get x equals -1 as a solution. And then you've got x minus 2 equals 0. And you add 2 to both sides, and you get x equals 2. And that was the two different things. So then, of course, the x-intercepts, which I have to stress, again, are points, will occur at the points. What you plug in, -1, what you get out, 0. That's what we said. What you plug in, 2, what you get out, again, 0. So those are the two intercepts for it. Hey, cool. That's all there is to that. Now, let's go ahead and talk about the y-intercept down here. And it's exactly the same way as always. So to get the x-intercepts, you set it equal to 0 and solve. To get the y-intercept singular, there's only ever one of these. And if you can't remember why there's only ever one of these, because if there's more than one y-intercept, well, the thing that you've got isn't a function because it fails the vertical line test at the y-axis. So the y-intercept will always be singular. X-intercepts might be singular, in this case usually plural for rational functions. But sometimes there's no x-intercepts, but we still say x-intercepts. There's 0 x-intercepts. It's still plural for that. English is weird. So to find the y-intercept, you just plug 0 into the function. That is, your input is 0. Your input is 0 for you to be on the y-axis. You went from here, you went neither right nor left. It had to have been 0. So for you to be here, your x had to have been 0. For you to be here, your x had to have been 0. So we plug in, because x is always an input, we plug in x equals 0, and that's it for that. So to find the y-intercept, we just plug in 0 to the function and solve. That is, we find f of 0. So you literally just plug in 0. So in this function, you just plug in 0. And that's it. So we plug in 0 everywhere there's an x. So there's an x there, and there, and there, and there. So you plug it in everywhere. So there, and there, and there, and there. And you do all the math. 0 plus 1 is 1. 0 minus 2 is -2. 0 squared is 0. Minus 10 times 0 is 0. Plus 25 is 25. 1 times -2 is -2 over 25. That's your final answer. So the intercept is a point, and it happens at the point what you plugged in, 0, what you got out, which is -2/25. So it's a weird number, but that's it. That's how you get the x and y-intercept for a rational function, and it's how you get it for literally any other real defined function. You just set it equal to 0 and solve to find the x-intercepts, plug in 0 to find the y-intercept, because that's what you're doing graphically. So I like it when math makes sense, and you should too. So that's the x and y-intercepts, and that, well, that isn't what makes this function weird. And I do call these weird functions because they do look strange. And we're going to graph one here later on when we do some actual written examples. But I do want you to see the theory behind all of this. So let's move on and let's talk about asymptotes, the things that make radical functions, well, radical. So let's start with the vertical asymptotes, the up and down of the asymptotes. To find the vertical asymptotes, we set the denominator of the fraction equal to 0 and solve. We do this because the function breaks and has those asymptotes at the points where we divide by 0. So, looking back at our function, we have f of x is x plus 1 times x minus 2 over x squared minus 10x plus 25. So we have to solve the denominator equal to 0. So you're going to have wild behavior in your function anytime that you divide by 0, because dividing by 0 does weird stuff. It just does. So what's going to happen is you're going to have some limiting process where you're going to positive infinity or negative infinity. And we'll literally talk about this in calculus. But before we get there, we've got to talk about all this other stuff. So what's going to happen at these points is you're going to have asymptotes. So here's sort of a preview of what these functions are going to look like. But here's an example. So let me get an x and a y axis. Okay, and let me go over here and get a different color to draw this. Let's just do it in white. So what's going to happen with some of these is, let's say that you've got your asymptotes. And let's say, not for this specific example, this is a completely different example, but what will happen is you'll have asymptotes at who knows how many points. Let's just do 1 for this example. And then let's actually graph this thing in red. So your function is going to, for instance, come along and come down. This is just an example. And touch. And then perhaps come along up here as well, like this, and then come up past this asymptote here as well. And I can extend this asymptote around a bit, all the way through the text. But you see what we're talking about. So it's like there's this divide where this thing wanted to be doing something, but it's got to come and go down towards negative infinity in here and up towards positive infinity here. And it's going to have that sort of weird behavior, but this is a vertical asymptote. And that means that at this point, whatever this point is, we'll call this point P. At point P, that is, there's an x minus p factor somewhere in the denominator of this function. The top of this is just some function in general divided by x minus p. It is going to look like this. It's going to have this asymptote here, because if you plug in p, of course, you get p minus that point p in the denominator, which is 0, and you're dividing by 0, and, well, it's going to break your function. This is what we mean by break your function. It literally breaks it. It goes from being over here to suddenly being over here and doing this thing. It breaks it in half and melds it around a bit. And that's not weird. It behaves exactly like we think it should, as in it's broken there because we're dividing by 0. And I think I've probably belabored the point on this enough. So let's go all the way back and look at this. So our function, obviously, let's get this back to a nice blue. Our function is going to break whenever this term equals to 0, because that's the denominator. So what we're going to do is we're going to say, okay, well, where does it equal 0? Because wherever it equals 0, that's where your vertical asymptote is going to show up at. So we just take that thing in the box. Here it is. We set it equal to 0, and we solve. So we know that x squared minus 10x plus 25 factors is x minus 5 times x minus 5. Clearly. Minus 5 times minus 5 is 25. Minus 5 plus minus 5 is negative 10. So it's going to factor nicely, which means that we're solving this. Okay? So we get x minus 5 times x minus 5 equals 0, which means that x equals 5 is the equation of our vertical asymptotes. So the fact that it happens twice, that the multiplicity of the answer is 2, it doesn't matter when stating the equation of the asymptotes. It's just the same line laid on itself, so we only count it once. But what we mean by this, when we say the line x equals 5, we mean x is always 5, which means this. You come out here to 5, like this, and this is the asymptote. It's x is always 5. Why? Well, y can be as big or as small as you want it to be, but the x is always 5. That's the line, which means that your function, and I don't know what this function looks like exactly. I could do the rest of the math, and I believe we will do the rest of the math here in a minute to sort of see that sort of thing, but it could look something like this. Maybe. We'll see. Okay? Something like that's what we're talking about. So it will approach from either side, and we'll see how to get all the rest of this stuff done here in the future. But that's the sort of thing that we're talking about with this. So to find the vertical asymptotes, just to recap, what you do is you take the denominator and set it equal to 0. And solve. Why? Because vertical asymptotes occur where the function breaks, And the only way that these functions can break, since they're rational functions, the only way you can break a division is dividing by 0. So just make it so that you divide it by 0. Make it so that you divide it by 0. And then whatever you get for your answer is the equation of that vertical asymptote, because x equals something is a vertical line. Y equals something is a horizontal line, by the way. All right, that's vertical asymptotes. So we've covered 3 of the 4 big topics in here. So I want to go talk about horizontal asymptotes, the last of the big topics, and then I believe we get into end behavior a bit and talk about it as well. So let's talk about horizontal asymptotes now. All right. For those of you taking notes at home, thank you. For those of you not taking notes at home, I advise you to rewind and, well, take notes. This is hugely important, and there's a lot of stuff that can happen with horizontal asymptotes. It's not that complicated. And for those of you trying to read ahead while I'm talking, stop. Just listen for a second, and I'll explain this to you. But if you want to go ahead and copy all this down first and then come back and watch it, that's fine. There's a lot of stuff here, but it is actually not that complicated. So to find the horizontal asymptotes, rather, there's usually just one for us. We look at the degree of the numerator and the degree of the denominator. There's only 4 cases between the degree of the numerator and the degree of the denominator. Case 1 says this: if the degree of the denominator is greater than the degree of the numerator, then the horizontal asymptote happens at y equals 0. Always. So if the degree of your denominator is greater than the degree of your numerator, the horizontal asymptote happens at y equals 0. Always. That is to say, if I had something like x squared minus 3x plus 2, okay, over x cubed minus 4, this thing's horizontal asymptote will occur at y equals 0. It is the x-axis. It will have a horizontal asymptote at y equals 0 because the degree of the denominator is 3 and the degree of the numerator is 2. It does not matter that this thing's missing a bunch of terms. Doesn't matter. It will always be at y equals 0. Easy enough. So, let's talk about the next case, which is if the degree of the denominator is equal to the degree of the numerator, the horizontal asymptote happens at y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Let's say, for instance, that we had 3x squared plus 2x plus 5 over 2x squared minus 4x plus 20. Okay? The degree of the top is 2. The degree of the bottom is 2. All right? Which means that your horizontal asymptote is going to occur at y equals 3 halves. So you go up 3 halves, 1.5, on the y-axis. You draw a horizontal line through that, and that is going to be where your horizontal line is. So that's case 2. So that's 2 cases, and those are the easy 2 cases. The hardest of the 4 cases is case 3, and it's not even close. If the degree of the denominator is less than the degree of the numerator by exactly 1, then we have to use synthetic division to find the slant asymptote. All right, forgive me here. Synthetic division to find the slant asymptote, which is the horizontal asymptote except slanted. To find it, simply discard the remainder, and we will have the equation of the line of that slant asymptote, and we'll do an example on this in a minute. But if the degree of the denominator is less than the degree of the numerator by exactly 1, that is, you've got something like, for case 3 here, like x squared plus 1 over x minus 4, like that, then this is less than this by exactly 1. 1 is exactly 1 less than 2. Or maybe you've got x cubed plus 3x plus 1 over x squared plus 4. This is less than by exactly 1. And in this case, since you're dividing by a squared term, you wouldn't even be able to use a synthetic division either. You'd have to use polynomial long division, but you won't see problems like that from me, I can assure you. But in this case, you're going to have something called a slant asymptote, which is real weird, but we'll go over that a bit more in a second. But that's why we learned synthetic division, was to deal with this sort of thing. All right, and then there's case 4, which we're not going to consider too much. But case 4 is if the degree of the denominator is less than the degree of the numerator by more than 1. That is, the degree of the numerator is way bigger. It's like x to the 15th, and the denominator is like x squared or something. Its horizontal asymptotes, we'll talk about its end behavior and all that using the tools developed in calculus. So we'll just push that to calculus, and we'll talk about it then. No big deal. We have better tools then to deal with and to talk about its end behavior. Some really heavy lifting can be done with some very easy tools that we can develop in that class. So let's move on from here. So if you don't have this copied down, I'd pause it and copy it down. Otherwise, we're moving on. So now let's recall our function and note that the degree of the numerator equals the degree of the denominator, and this will fall under case 2. So what we're saying is our function was x plus 1 times x minus 2 over x squared minus 10x plus 25. That hasn't changed. All right. So I just put the 1s out front here so that you can see them. There was a 1 out front. So the degree of the top is 2, and the degree of the bottom is 2. The degree of the top, the degree of the bottom is 2. We can see that pretty easily. And we know that if we FOIL this out, that is, we just take just the leading terms and FOIL this out, that we're going to have 1 times 1x times 1x. X times x is x squared, and we know that's going to be the biggest term, times 1 is 1. So we know that both of these have degree 2. That's why I can say that this degree is 2. I just multiplied it out in my head, and you just have to do the terms with the x's in them, the first terms, the term you know is going to be the biggest. So then the horizontal asymptote is the line y equals 1. So y equals 1 is the equation of the horizontal asymptote of f, which is this. If you go up to 1, there'll be a horizontal asymptote here, which means that our graph, when it does its graph stuff, is going to approach that point but never quite touch it. It's going to do something like that. Here's the short of it. Here's all of the notes condensed down into one little thing for you to write very quickly. I know that it's possible for you to go find these notes that have already been typed up for you and have them ready, and that's all great. Please write this down. If you write nothing else down the entire time, write this down. Horizontal intercepts. To find the x-intercepts, you set the numerator equal to 0 and solve. The answers are coordinate pairs because you wanted intercepts. To find the vertical intercept, the y-intercept, you plug in 0 and solve. The answer is a single coordinate pair. It's 1 point. That's how to find intercepts. For any functions, by the way, any functions. To find vertical asymptotes of a rational function, you set the denominator equal to 0 and solve. The denominator equal to 0 and solve. The answer is one or more lines, x equals k, where k is just some number. They will always be, x equals k will always be vertical. They'll go up and down. To find the vertical asymptote, you set the denominator equal to 0 and solve, because if the denominator of a fraction is 0, something bad happened there, because you're dividing by 0. What's bad? How do we do that on a graph? That's an asymptote. It's a point it can never get to, because if it got to it, you would be dividing by 0. That makes sense. That's the first 3 things. Then there's the horizontal asymptote, and this is as put together as I possibly can for you. To find the horizontal asymptote, you use the degree of the numerator and the denominator to determine what to do. The asymptote is at y equals 0 if the denominator is bigger. It is at the ratio of the leading coefficients if the degrees are the same, and there's a slant asymptote if the degree of the denominator is exactly 1 less than the numerator. The answer is some line y equals a, where a is just some number. It will always look like y equals a, where a is just some number, except in the case of a slant asymptote, in which case it's going to look like a line. It's going to look like y equals mx plus b if it's a slant asymptote. Otherwise, if it is in fact a horizontal asymptote, then it will always look like y equals a. So that's everything. So please, get that down. I'll give you a second. You can pause the video and then come back and we can do some examples. Given the function f of x equals x minus 3 over x plus 4 squared, we want to state its domain, find its x and y intercepts, and state its vertical and horizontal asymptotes, and state its end behavior. Easy enough. So, in order to find the domain of this thing, all that we're going to do to find the domain, we want to know the domain, is we're just going to say, okay, let's take the bottom, the denominator there, square it, and set it equal to 0. Because if this denominator is equal to 0, hey, guess what? We've divided by 0, and that's bad. So we want to get everything but that. So we have to figure out what that is. Well, clearly, if we plug negative 4 into this, we're going to get 0 squared, and that's 0. That's your solution. So then we want to throw out negative 4, right? So how do we do that? So to throw out negative 4, we're going to write everything but negative 4. So everything but negative 4 looks like this in interval notation. That's the domain. The range we'll worry about in calculus. So now we just want to find its x and y intercepts. To find something's x-intercepts, you set the entire function equal to 0 and solve. But remember what we talked about earlier. In order for this function up here to be equal to 0, the x minus 3 over x plus 4 squared, the whole thing to be equal to 0, the numerator has to be equal to 0. Think about every fraction you've ever seen. If the fraction's going to be equal to 0, it has to be in the numerator. Because if the denominator is 0, then we've divided by 0, and that is definitely not 0. It's in fact quite the opposite. So we're going to set the numerator equal to 0 and solve to find the x-intercept of a rational function, because it's the exact same thing as taking the entire thing, like this, and setting it equal to 0, which is how you find the x-intercept for everything else. The only way that this can happen is if the numerator is equal to 0, so x equals 3 must be the x-intercept. That is, the x-intercept is the point 3, 0, and there's only one of those. So to find the y-intercept, you plug in 0. It's the same always. So to find the y-intercept, we're just going to plug in 0, and we're going to get negative 3/16. I can tell just looking at it. But look, we're going to plug in 0. So it's going to be 0 minus 3 over, like this, 0 plus 4 squared. And that's going to equal, well, 0 minus 3 is negative 3 over 0 plus 4 is 4 squared is 16. So the y-intercept then is going to be the point. You plugged in 0, you got out negative 3/16. Okay, so we found the domain, we found the x-intercepts, we found the y-intercepts. Now all we need to do is state its vertical and horizontal asymptotes, and that'll help us with its end behavior, what it does at the end. So let's find its vertical and horizontal asymptotes. So x minus 3 over x plus 4 squared. X minus 3 over x plus 4 squared is the function. F of x here is what we're working with. So let's think about this. We want to find its vertical asymptotes. To find the vertical asymptotes, it's where the function breaks at. And since you've already found the domain, it's going to be at all the x's that you threw out. Because to find this, all you're going to do is take the denominator and set it equal to 0 and ignore multiplicities. So we're going to get x equals negative 4. That is the line of its vertical asymptotes, because vertical asymptotes occur at the same places that aren't in the domain, because, well, you're dividing by 0 there. You can't divide by 0, so you throw those out. So those lines, x equals whatever those are, is where the vertical asymptote's going to show up at. And that leaves exactly the horizontal asymptotes and end behavior. So let's do the or the horizontal asymptotes. To find the horizontal asymptotes, what you have to do is look at the degree of the numerator and the denominator. If I FOIL this out in the bottom, I get an x squared term. Up here, I get an x term. So if I do the math on all of this and I FOIL this out, I'll get an x squared term in the bottom. So the degree is 2 in the bottom. On top, it's 1. The degree of the denominator is greater than the degree of the numerator. That's case 1, which means that our horizontal asymptote is going to occur at y equals 0, because this is case 1. If you don't remember what that is, go look back in your note. But remember, this has to do with the degree of the top and the degree of the bottom. So the degree of the top is 1. The degree of the bottom is 2. If I FOIL this whole term out, I'll get x squared plus 8x plus 16. And that is a degree 2 polynomial on the bottom. Since 2 is greater than 1, we have a case 1, so our horizontal asymptote occurs at y equals 0. It's just a matter of looking at and memorizing those cases. And then the end behavior that we want to look at. The end behavior that we want to look at is very simple. When the horizontal asymptote is y equals some number, the end behavior is always going to look like this. So we can do the end behavior super easy. The end behavior is always going to look like this. Since the horizontal asymptote looks like this, let's think about what this looks like for just a moment. I'll draw it over here. I'll draw it down here. Why not? It's going to look something like this. Okay. What we're going to do is we're going to approach 0 like this with some vertical asymptote wherever we've got our vertical asymptote at, -4 or whatever. This is an example of 1 over x. This is a sketch of 1 over x, which is the simplest rational function. But you can tell what's happening here is as we go to positive infinity, our graph is cozying up to 0. And as we go to negative infinity this way, our graph is again cozying up to, but never quite gets to, 0. So this is going to be some really weird looking stuff here, but we can say as x goes to negative infinity, our y's approach 0. That is, they approach the horizontal asymptote, and it'll always be like that. And it does it in both directions. So as x approaches positive infinity, our y approaches 0. Now we can also talk about this vertical asymptote here, and we can say as x approaches -4, are we going to positive infinity or negative infinity? And the easiest, quickest, dirtiest way to do that is with a table, but that's not what end behavior is concerned with. End behavior is concerned with behavior at the ends of the graph, specifically the x ends of the graph in our case, and that's what we're going to talk about. So that's the end behavior of a rational function. That's everything. We've found everything.